This is TechSNAP, episode 415, recorded on October 24th, 2019. Hello and welcome to TechSNAP, Jupiter Broadcasting Systems, Network, and Administration podcast. My name is Wes, and of course, I'm joined by Jim.
What's up, everybody?
Jim, you and I both have been having a lot of fun playing around with ZFS en route with the latest Ubuntu release. And since our last episode, Chris and I have been doing some benchmarking over on Linux Unplugged. Now, in our cases, we were just trying to find out what using ZFS en route might look like compared to ext4 on just sort of a run-of-the-mill mainstream laptop. And we use the Phoronix test suite to just run some basic file system benchmarks, get them over on open benchmarking so the audience could compare. We got a lot of great and interesting results out of that, some nice graphs to look at, and also a lot of data. And I was realizing we didn't really do a good breakdown of that. We didn't go into a lot of the terms and what it really means for a file system to be faster and in what terms you might actually care about to measure speed. Right? We've got terms like IOPS and throughput, and there's a lot to consider when evaluating the performance of a disk. So I thought you and I might have a conversation today about how you approach disk benchmarks.
Well, Wes, I hope you didn't think you were going to get through this without a car analogy.
Oh no, I'm sure I won't.
Yep, it's old gearhead time, kids. Buckle up and drag the chairs around and listen. So this really is one of those places where, for those of you who have ever been really interested in make car go fast, there's a very useful analogy to be made here. Back in my day, I was a big shade tree mechanic and I liked making the car faster and, this and that and the other. And you discover amongst car enthusiasts, there's several levels of understanding about how to talk about how powerful a motor is, right? So the most basic is you get the kid who he reads the latest Car and Driver and he gets super excited and he tells you the new Camaro's got 400 horsepower. The next level of understanding is the guy who looks at the kid, shakes his head sadly, and he says, that doesn't matter. It's not about the horsepower, it's the torque. Your third level of understanding is the guy who will tell you, okay, so those are related measurements, and what torque actually refers to is foot-pounds of force, and what it really means is basically how hard the motor can push to go faster, to make the wheels spin faster than they already are. And horsepower is a measure of work. It actually translates directly to kilowatts, just like you would talk about power in your home. And you can talk about that in terms of top-end speed. So if your motor makes 400 horsepower, that means it can do 400 horsepower worth of work at the absolute top end in pushing against the air and the rolling resistance on the road. And so if you don't have any more horsepower, you can't go any faster than that, regardless of how much torque the engine develops.
Right.
Now, your last level of understanding is the guy that understands that yes, that's true. And yes, these things are related, but it's actually very useful to talk about both things in different ways and for different things. Now, for hard drives, it's just like that. You've got your torque and you've got your horsepower. But in this case, it's IOPS and throughput. And much like torque and horsepower, you're reasonably well-seasoned sysadmin, storage engineer types, they'll tell you, it's usually all about the IOPS. And again, much like torque, when you talk about IOPS, you're talking about, what in our car guy days, we would call low-end grunt. You're talking about when things are difficult, like when you're just getting off the line in that car, or in terms of storage, when you're performing really difficult operations that make everything bogged down.
Right. I mean, IOPS, input-output operations per second, that's what you're talking about. This is a low-level operation, a transaction with the disk.
Exactly, and throughput is megabytes per second, how much data you're actually pulling off the disk. Now, again, much like torque and horsepower, they're really not static measurements. When you talk about throughput, you're usually talking about throughput under the absolute most optimal conditions for the disk. Now, you don't have to be. You can talk about throughput when you're doing 4K random I/O, and you can still talk about that in megabytes or kilobytes per second, and you can compare one system that has lots of IOPS to another that has lower IOPS, and you can still get lots of megabytes per second versus lower megabytes per second. But it becomes more useful to actually think about it in terms of the IOPS. And the other thing about that, again, much like our car analogy, It's usually more useful to talk about the IOPS just like it was for the torque because we usually do care more about that bottom end. We care about when things have really kind of bogged down. Now, Wes, you remember, laptops without solid state disks, right?
Oh, yeah. I mean, I've been trying to forget.
Sure. But you're using your laptop and everything seems fine and you're moving files around and you're copying stuff and you're happy, right?
Yeah.
So yeah, you're doing your stuff, you're copying files, you're happy. Now, honestly, that laptop drive, it's a piece of crap. It's got terrible throughput. You're lucky if that thing will do more than 60 or 70 megabytes per second, where your desktop disk might do, 110 megabytes per second, but you don't care. Because right now, you're doing relatively contiguous sequential type operations. You're not asking the disk to seek around a lot. But then, something happens. Maybe Windows or Linux's search indexers kick in and start kicking up a lot of drive activity where they're looking back and forth and doing a bunch of things. Or maybe you have an update process kick in. Or maybe you start up a database. At any rate, what's really happening now is now you're dipping down towards the worst case scenario for throughput. You're looking at 4K random IO, where you read one 4K block of data at a time, and then you ask that disk to seek to another area on the disk where you incur this big latency penalty in between the one operation and the next. So your IOPS goes in the toilet, your throughput goes in the toilet with it.
Right.
But the thing is, if you'll remember, we didn't really care what our throughput was up there at the top end where the manufacturer likes to claim those big numbers. You don't care. It's big enough. You're happy. But then when your laptop sounds like it's grinding coffee in there, and you're lucky if you can get a menu to pop up when you click a button, that's when you're super angry. And the real issue that's happened there is your IOPS has gone way low, which has then taken your throughput with it.
That's why people say it's all about IOPS.
Absolutely. And, to be clear, again, like torque and horsepower, these things happen on a curve. You don't just have one torque rating for an engine. You have it across a range of RPMs. And you don't have just one IOPS rating for a disk, really. If you're doing very large block operations where you've got lots and lots of throughput, you're probably not actually going to be getting many IOPS out of that disk right now because you are actually bottlenecking on the throughput. You don't need to move the head around if it's a rust disk or just, issue different IO operations on a solid state disk because you're pulling tons and tons of data for very large operations. So you're not necessarily consuming that many IOPS then, but you are still getting a ton of throughput. Whereas way down on the bottom end, you may be consuming tons of IOPS and not getting very much throughput. It's all kind of complicated.
Right. It depends a lot on the workload and what you're trying to achieve.
Exactly. And again, the thing that I really try to impress on people is that the only workload you're very likely to care about is the one that your storage is bad at.
Of course.
Very few people really notice the difference between a conventional hard drive reading 110 megabytes a second and a solid state disk, reading 300 megabytes a second. You don't really notice that difference that much. You don't really care. Everything's trucking along. You're happy. Where you really care about is where, you're doing a very heavy random IO workload, and now that solid state disk is only producing, maybe 40 megabytes a second instead of that 300. But the Rust disk, it's only producing like 800 kilobytes per second now under that same really heavy IOPS workload. So, the performance dropped on both of them, but on the solid state drive, it's still in that territory where you're basically happy. You're moving a significant amount of data. Things are visibly happening. Everything hasn't crawled to a halt. But on that Rust disk, it's just fallen off a cliff and nothing happens, nothing works, and you want to throw your laptop through the window.
Don't do that, though, because then you'll probably get 0 IOPS. All right, well, that clears up some things about IOPS and throughput and when we might care about which. How do you go about actually measuring them, though, especially with any certainty?
So there are synthetic tools that are good for that. One mistake that you see a lot of, I hesitate to say Linux newbies, but you see a lot of Linux folks making is they have access to this tool DD.
The infamous DD.
The infamous DD. Now, the thing about DD is, yes, it absolutely will just, barf a bunch of data in a sequential pipeline on or off of a disk. But, like we talked about earlier, you usually don't really care much about that sequential performance. Whatever it is, you're almost always happy with it unless you're building a very specialized application. What you care about is when you get down in the weeds with that random IO and all of a sudden everything falls off a cliff, including any sequential workloads that you might be trying to do in parallel.
Right.
Because there is no such thing as a sequential workload sitting next to a random workload. They've both become random. Everything drops down to the lowest common denominator. So now we know that DD is not a very good tool to measure this. The question becomes, what is?
Right.
And there's a fabulous cross-platform command line tool called FIO. It's just great for this.
FIO. I saw that as part of the Phoronix test suite when I was watching it go.
The thing about that, though, is, so it's part of the test suite, but the question is, what are you doing with it? FIO is not something that you just run and you say, oh, well, these are my FIO results. FIO is a way to model disk workloads. So the question is, what workload are you modeling with it? And you can make FIO do just about anything that you want to. Do you want to test 4K random writes? Do you want to test a mixed workload of 4K random writes with sequential reads? Absolutely, you can do that. Do you want to use QDEP 32, QDEP 1, anywhere in between? Do you want to sync after every n block operations, or do you just want to pause the test for a full sync at the end of it so that you don't end up with, false results because the disks are actually still chattering away and writing after your workload is technically done? You can do all these things. It's all in the arguments that you feed it, or if you've got tons and tons of arguments, the config file that you read with it when you invoke it.
Okay, well, Flexible IO Tester is a good name then.
It's exactly what it says on the tin. So with all that said, what do we do with FIO? And my answer still is that, most people, you don't want to bury yourself in data that you don't really understand and isn't necessarily relevant, right? And that's a complaint that I actually have with a lot of Phoronix's benchmarking. Laravel he generates a lot of good data, but there's not really a lot of valuation done, and it's very easy to look through all of it and just kind of get lost and not be sure what you're looking at or for or why.
Right. There's not always interpretation along with it.
So I get right back to, my idea of, I want to adhere to that KISS principle. Keep it simple, stupid. So when I use FIO, I generally try to simplify it down in a few ways. For one thing, I just don't bother looking at read operations. Unless you've got some really, really strange media, reads are always going to be either about the same speed or faster than writes, which tells you that reads are probably not going to be your bottleneck. Now, a whole lot of reads get serviced out of cache in real-world workloads. So a lot of your reads aren't really coming off the storage. So again, it's not necessarily the most benefit to benchmark the reads. So now that we've established that writes and reads are usually going to be about the same speed when they actually hit the metal, and if anything, the writes will be a little bit slower, so that's going to be your pain point, what we're left with is we can bypass a lot of our complexity by just ignoring reads and testing writes. Anything that we need to know about the reads that actually do get to the bare metal, we'll have probably learned well enough just by examining writes to begin with. And also now we no longer have to worry about, going to heroic measures to disable read cache to keep from ending up with results that are orders of magnitude faster than they should be, because, we just end up reading blocks once off the disk and then, 100 times off of cache in a long benchmark run.
Right. I mean, so many programs and operating systems have all worked hard to make sure that it's very efficient to do those reads, but it certainly can get in the way of benchmarking if you don't know quite how to turn that off.
Absolutely. It also means you may be able to run much shorter benchmarks and get more done in less time because, when we talked about having to make sure that you don't end up using cache, one of the ways that you do that on a system, if you're trying to benchmark reads, is you just have, a read operation that's tremendously larger than the amount of RAM in the system. Well, I don't know about you, but a lot of the time I'm running these benchmarks on systems with 64 gigs, maybe 256 gigs of RAM. I really don't want to have to run, a benchmark in the multiple terabytes just to be sure I'm not taking advantage of read cache and not really hitting the metal. So, all right, we've cut out half of everything. We've cut out a lot of our complexity by just ignoring reads and saying we're just going to focus on writes. You can't really cache a write. It has to go to the disk. The next step is you have to make sure that, yes, it really will go to the disk. Now, the argument for that is called end_fsync equals 1. Unfortunately, that's not set by default with FIO. So if you do a big write benchmark, particularly with a system like ZFS, you'll actually end up with greatly inflated results because what you'll notice if you pay attention, especially if you're using Rust disks, so you can actually hear this, You'll do a 5-minute FIO run and it will finish and you'll get your numbers, but you'll still hear the rust chattering like mad in that chassis for the next, 5 to 30 seconds. And those are writes still actually getting committed to disk, but they're not getting counted in the time in your benchmark, so your numbers are wrong. Now, if you do end_fsync=1, that means that FIO doesn't cut off the timer until the very last block has actually been committed to disk, and that makes sure you get accurate numbers.
Yeah, that seems like a good thing to catch there if you're trying to determine the actual total length of time it's really going to take.
Yep, it is hugely important. Before I understood about end_fsync=1, I was just kind of trying to run really enormous write benchmarks again to minimize the impact, of those extra few seconds of writes that were still chattering to the disk after the time was done. So like it's a fairly small impact if you've been running, like a 15-minute benchmark and you've got an extra 5 to 30 seconds of writes. But, if you're running a 2-minute benchmark, then it's enormous.
Way more noise than you want.
But if you just use end_fsync=1, you don't have to worry about that.
Nice.
So the next thing, we've talked before, I said, you care about IOPS because what you care about is when your system makes you mad and you want to throw it through the window.
Exactly.
I'm a big believer in you test the pain points. Who cares about that top end? It's like, again, I'm going to go ahead and drag us back to that car analogy. You talk to your good old boy or girl that just wants a super fast car they can drive around. Well, you don't really care if that car can go 300 miles an hour because when are you going to do that, right? What you care about is getting off the line, stoplight to stoplight, the speeds you're actually driving at. You want it to feel fast. You don't want to be like, oh man, I stepped on the gas and I'm just like waiting and nothing's happening and this sucks.
Right. And that might be where some of this changes depending on your exact workload case. Maybe if you do have a rare case where you really do need the fastest top end because that's your special use case, okay, you change some of how you're testing. But for most day-to-day use, you're never going to get there.
That's the thing. For most folks, you don't even actually want to test your normal workload because that's when you're happy. You don't need that to change. You're already happy there.
Or at least I hope you're happy normally.
Yeah. You want to test the parts where everything sucks because you want to minimize that pain point. That's going to be your 4K random IO. So now we say, all right, we're not really going to bother with sequential unless we just, if you're writing this up for publication somewhere, you may have to write that just so you can put that number because readers are going to complain about it.
Right.
But, if you're doing this, on like a work basis or even just a personal basis where you really want to optimize your stuff, you don't care about sequential. You just don't. I mean, one example where you might care about the top end is you are building a very dedicated purpose server that the only thing it does is serve as an rsyslogd target, right? You've got 50 other machines sending logs to this thing, and the only thing it has to do is barf all of this stuff onto disk in a very straight line. It almost never reads anything back even. It's just writing all these logs to disk, and that's all you care about. Now, in that case, sure, you do care about throughput because throughput is what means you can add more machines to this total that are, sending logs over the network to this server. But that's a very unusual use case for most of us, and particularly anybody who's doing any desktop use. What you really care about is that 4K random IO because it happens more frequently than you think it does. Most of your day might be moving files, from 1 meg, 5 meg, 10 megs in size. But I mean, there are literally thousands of times a day that you're reading tiny little dot files in your home directory. Or, if you're on Windows, you're reading all these tiny little libraries and writing to tiny little garbage temp files and C Windows temp that will never get deleted until you go in and manually clean them out after a year and you've got 300 gigs of them. But the point is, these are all the times when your system is making you mad. So that's what you want to improve, and that's what you want to benchmark. So now we've actually gotten ourselves narrowed down to one pretty simple, pretty easy to understand basic benchmark. We run FIO. We only test random writes. We test at 4K because that's where the worst pain is.
Right.
And we set end_fsync=1.
That sounds pretty simple. I mean, I think I can handle that.
And again, the really great thing about that is that because that one test really does cover the pain points and you can readily and accurately infer so much other information about it, about, the few cases with pain points that it doesn't necessarily cover, like, when you actually do have to read from disk, it's going to be roughly similar. Now, we've got what the manufacturer specifications, the manufacturers like to say, oh, this disk will do 150 megabytes a second. This solid state disk does 489 megabytes a second. Well, obviously, again, that's the best case. That's the biggest number. It looks sexy. The idea is that you can say, well, this one is great because it has a bigger number, but we now know it doesn't really work that way. But you go look at that 4K random IO number on writes, and you actually do have one number, and you can just compare that one number between disks or between storage systems. Maybe you're talking about different RAID topologies, and now you can really say, okay, this one is going to work better for me than that one does.
I like that, right? So it's one number you can actually use. You can compare it between different systems, different setups, different disks, and have something that you can reasonably relate between them to determine how well is this actually going to work for me.
Absolutely. So, like in a desktop scenario, your 4K random IO, the number you get out of FIO, it might be pretty small. If you're on an inexpensive consumer solid state drive, you might not be seeing more than, it might be as low as, 10 megabytes a second when you're doing this. And the reality is that most of your usage of that system, you're going to be moving more like, 50 or 60 megabytes a second. And that's fine. It's just, again, the point is that you don't measure the thing that is happening most of the time that you're happening with. You measure that pain point.
We've talked a lot about spinning Rust, old style disk drives. And I know there's a lot of architectural differences between SSDs and those older style drives, right? And that comes up a lot of times when you're benchmarking or considering workloads. So does any of this advice change for modern SSDs?
Not exactly. There are absolutely enormous architectural differences between the two. The biggest lure of solid state disks compared to conventional Rust disks is you lose that seek penalty. When you do random access on a drive, you're literally asking it to move a head physically around.
It's a lot of work.
Yeah, well, it's like picking up the head on a record, and I'm probably dating myself again, but an old school LP, you got to pick up the needle and reposition it. Yeah, that takes a while, right? It's the same thing on a Rust hard disk. Now, solid state disks don't have that problem because everything is solid state, which means electronic with no moving parts. And they don't necessarily have an enormous penalty with moving around for random IO. However, you would also be mistaken to think, well, then a solid state disk should always be, as fast with random as it is with sequential because there's no seek penalty, right? No, not so much, but the reasoning behind it is different. Your issue with small block operations on a solid state disk is that you're minimizing the parallelism. Solid state disks, the underlying media is not actually as fast as the whole disk because even a tiny little consumer SSD, it's not really one disk the way one consumer laptop Rust hard drive is one disk. An SSD is actually a RAID array of the underlying flash media. The individual flash elements underlying that you're reading from or writing to, they're not that fast. Where you get the big top end speed from the SSD, where you see that 300 megabytes a second or 500 megabytes a second, that's when you got a lot of parallelism and you're actually reading or writing data from all of those underlying flash elements at the same time.
So is this what sort of where the controller comes into? We've got a lot more complicated machinery going on under the hood in the disk itself to accomplish these things?
It does, but at the end of the day, there's nothing that the controller can do to really account for the underlying problem that if you're only asking for one page worth of data, it's only going to come from one piece of the flash media and you don't take advantage of that parallelism to accelerate things.
Right. There's just no parallelism there.
That's where you get into queue depth because you may have noticed I mentioned that word earlier. That's one of the things you control with FIO. Queue depth 1 is going to be your most punishing setting because that means you're not going to ask for the next 4K block until you've gotten your answer on the first one. Now, if you've got queue depth 32, you can actually ask for 32 of these 4K blocks, which are randomly located, but you can ask for them all at the same time. Now, that allows your SSD, when those individual blocks or pages are actually stored on separate elements of the medium, now it can actually pull those off in parallel, or if you're writing, it can write them out in parallel, just as though you'd been doing a larger operation to begin with, so things speed right the heck on back up again.
Right, so this is a difference of, one big task reading a huge file off the disk maybe versus all sorts of other tasks going on and reading from different files located in different parts of the file system.
Right, and now increasing queue depth is also helpful for Rust storage, but it's nowhere near as helpful as it is for SSDs because there is a single Rust disk can't truly read or write more than one block at a time. Increasing the queue depth there will help because it gives your drive and your file system kind of more room to play around with ordering these things in a way that makes sense. So maybe you can draw kind of a straight line, even if there's individual skips and hops. It goes in a sensible way when you're reading the next 32 elements if you asked for them all at once. Whereas if you'd asked for them one at a time, then you might literally be skipping from one end of the disk to the other and then back to the first one and back to the other one in a really terrible way.
Right. So this is where like smart disk scheduling algorithms can come in.
Exactly. Like, imagine, we're going to go back to the car analogy. Imagine you're driving from my house in Columbia, South Carolina, out to the studio in Washington State. Now, if you also had stops to make, in Georgia and Arizona and, say New Mexico, you draw a straight line in between them. It's a very different proposition for you to say, well, no, you need to be at my house, then you need to be the studio in Washington State, then you need to be in Georgia, then you need to be in New Mexico. Well, that's going to take a whole lot longer, right?
Oh, yeah.
That's the difference between having a wide queue depth versus a narrow one. When you've got the narrow one, you have to fulfill that one thing right then, no matter how dumb it is. When you've got a wider one, you've got a chance to arrange everything in a way that makes more sense. But that's for Rust. Again, on solid state, when you've got the wider queue depth, you literally have the chance to pull from more of the underlying media at once or push to it, which will go a lot faster. Wes, I will mention one other thing that's different about testing Rust versus testing solid state disks. On Rust, as long as you've got end_fsync equals 1, it really doesn't matter much how long your write benchmark is. It's not generally going to speed up or slow down much. It's just going to kind of be what it is and be done with it. Now, solid state is a good bit more complex because with solid state disks, particularly consumer ones, like I like Samsung's line, the Samsung Evos.
Yeah, I have a few of those myself.
Before we can really explain the difference between the Pro and the Evo in a meaningful way, we got to know a little bit about the underlying medium structure of solid state disks. Now, the first SSDs, they utilize something called SLC flash. SLC stands for single layer cell. What that means is you can only store 1 bit in each individual physical flash cell. It's a 0 or 1. That's all you got. SLC is it's very high write endurance. It's very high performance, but it's also quite expensive. So SSDs didn't really take off in the consumer space until the advent of MLC. Now, MLC stands for multi-layer cell, but really it should just mean 2. It sounds like that would mean anything more than 1 bit per cell, but it really very specifically means 2 bits per cell, and that's it. That's what your first consumer solid-state disks were made from. Like I deployed a whole lot of those Intel X25M 80 gig SSDs back in the day, and those were all MLC flash. Now, when we get down to the Samsung Evo, those are TLC flash, tri-level cell, and that means you got 3 bits that you can store in each individual cell. Now, the thing about that is, every time you go up in the number of states that you can store in one of these cells, where you have more different levels of voltages you have to be able to reliably distinguish between, your cell gets lower write endurance, it gets lower. Nobody usually really uses the term read endurance, but the charge in a cell on flash will only stay stable for so long. And nobody really wants to be really concrete on this either. One of the jobs of an SSD's firmware is to detect when a cell is starting to go stale and to rewrite it. Samsung in particular had a nasty bug in their firmware for a while where Evos were not refreshing stale cells, and as a result, data that hadn't been read, or actually I should say data that hadn't been written to in a couple of years, it might take a long time to read that individual cell, because basically what's happening is it gets a bogus value that doesn't match error correction. It has to keep retrying it over and over and over until it gets the right one.
It's just hard to distinguish between the various levels like it's supposed to be able to.
Exactly. So now you're seeing, your nice super fast SSD, when you go to read very old data from it, the writes are still fine, but you go to read very old data that hasn't changed in a long time, and it's acting like a really, really cranky Rust disk that's on the way out, and for exactly the same reason. Because it's getting bad data that doesn't pass error correction. It's having to go back and reread it over and over and over again until it gets something that matches its ECC. Anyway, all these problems get worse the more different states you have to store in each individual cell. So we've gotten to TLC now, and TLC is cheaper than MLC, which in turn was cheaper than SLC, but we've given up something to get there. In particular, we've given up a lot of performance. In order to overcome that, Evo drives are not all TLC. They actually have an MLC cache on the front. And when you write to these things, for a while, you're going to be writing to the MLC. And then in the background, it will slowly stream that out from the MLC front end cache out to the TLC main storage cells. But if you do sustained writes, if you really get on one of these things, jump on it, and back to the car again, keep the pedal to the metal and keep that thing roaring for a while, all of a sudden you'll see the performance just fall off a cliff. And the reason for that is because you've exhausted that MLC cache, and now you're on nothing but the TLC on the back end, and you're also still trying to stream and commit those writes that you had temporarily in the MLC, as well as having to do all of your new writes directly onto the TLC, and it stinks.
Right. You've run out of all your fast buffer to hide the slow actual final data storage.
Exactly. Now, Wes, that's where we get into the difference between the Evo and the Pro, and why you would potentially want to spend that much more money on the Pro, because the Pro is all MLC. There is no TLC. The whole thing is as fast as the cache on the Evo. So basically, no matter how long you hammer it, it's going to keep responding the same, where that Evo just falls off a cliff after like 30 seconds or so of really, really pushing it. As I mentioned, the read and the write endurance is better on MLC than it is on TLC. Every additional state means that your data doesn't stay stable as long, and it means that it takes longer basically to set it properly. And it also means that your cell can't stand up to as many writes before it starts failing.
Is that what you mean by write endurance?
Exactly. There's only so many times that you can change the state on one of these cells before it starts to break down in quality. And you may still be able to energize it versus not energize it, but you're not as sure of exactly what voltage you're going to get on the thing. So the more different voltage levels you have to be able to reliably distinguish or detect, the sloppier that cell gets, the quicker you start having problems where it's not actually accurately taking this value that you're trying to write to it. Now, the Pro is all MLC. There's no TLC, so it lasts longer. So, if you want to be using that SSD for the next 10 years instead of the next 5, maybe you want to spend the extra 25% on the Pro.
Are there other considerations? I mean, are there some workloads that, mostly fit within that MLC cache on the Evo and would be just fine there?
It really just boils down to, sustained heavy workloads. It doesn't really matter much if it's random or if it's sequential. If you're going to be, in periods where you're like, hey, I've got like 10 gigs worth of data that I want to dump onto this SSD as fast as I can, Evos are not good at that. The performance is going to drop pretty rapidly. You're going to see this even worse where, in any situation where you need to read and write from the disk at the same time, like say, a file is in one user's home directory and you want to copy it to a different user's home directory. So you're simultaneously reading from the SSD and writing to the SSD, right? That's going to be some of your worst workload right there. And if you're doing that with, a whole bunch of data on a consumer SSD, like an Evo or, like most of the Crucials or SanDisk Ultras or you name it, yeah, they're going to fall off a cliff. Now, on the other hand, just your regular general desktop usage, you're just kind of doing normal things. You're just browsing the web. You're playing a game every now and then. You're not really worried about moving big files or doing really heavy database operations or whatever. You may be fine. You may never leave that cache, and you may literally see no performance benefit out of the Pro versus the Evo at all. Now, I will still say there's still the endurance benefit. You can't get away from that.
Well, thank you, Jim. I think I'm off to go do some more benchmarking and maybe some SSD shopping. That's going to do it for this episode of TechSNAP, but don't worry, you can find a whole bunch more over at techsnap.systems. You'll find our whole back catalog, easy ways to subscribe or get in touch. And if you like this show, make sure you check out Self-Hosted, a podcast with Chris and Alex exploring free and open source technologies you can host yourself. If you'd like more Jim, you can find him writing over at Ars Technica or on Twitter. Jim, you're
at JRSSNet.
I'm there too. I'm at Wes Payne, and the whole network is at Jupiter Signal. Thank you so much for joining us.
And we'll see you in a couple weeks.